All of these webinar um, series sessions are recorded and will be available to watch at a later time on our website. The previous sessions are on there already. Today is Thursday, November 20th. You can see the kind of schedule for the rest of the year and into 2026 here. Join us on Thursday, December 18th for the next one. That will be flight training focused. And then the calendar is on our website, airtap.umn.edu for 2026. We are in a Zoom webinar session. So you can see and hear us, the panelists and hosts, but we cannot see or hear you. There are a couple ways for you to participate. If you want to share an idea with everybody that's in the call, or if you want to let us, the panelists, know that you need technical assistance, you can do that through the chat function. Or if you'd like to ask the speaker or any of the panelists a question, please submit that through the Q&A feature. We will be monitoring the Q&A throughout the session. If questions are relevant to what's on hand at the moment, we can ask those questions. Otherwise, we will do one big, long Q&A at the end of the session. So without further ado, I would like to welcome Korum Ellis. He is the founder, the chairman, the CEO, and the product architect of FlyOnE Sustainable Aviation. And he joins us today from Perth, Australia. So Korum, I will turn it over to you.
Greetings. Nice to be here. And thanks for everybody that's chimed in. And I'll try not to look too tired. It is getting close to the middle of the night here. But thanks, guys, for getting me involved and reaching out. Hopefully, a few of the lessons we've been learning over the past few years might be insightful and helpful to the infrastructure developments and the new opportunities you guys are unlocking for operators and users in the area. We've been flying electric aircraft here in Western Australia since 2019, and a fun little known fact is we're actually the first in the world to get an electric aircraft certified for a commercialized use, which was pilot training for reward and hire. So we were able to integrate an electric aircraft back in 2019 to a flight school, a brave and enterprising flight school that was interested in making the space for us to try the new technology and working with the new equipment to see what sort of advantages it presented and, of course, what sort of challenges it would also present. So it's been an interesting couple of years, and we have learned many lessons. So the first aircraft that we integrated was, of course, the Pipistrel Electro. I'm sure a lot of you that have paid attention to the space are familiar with the Pipistrel. There are quite a lot of them in the States and in Europe as well, of course. Quite a few hundred now have been released and distributed by the factory in Slovenia. The aircraft is amazing. Pipistrel have been making aircraft for many, many years, and the Electro version of their very popular airframe is a very good example of an electric aircraft. However, it is quite limited in endurance. And I think that was a very deliberate move on Pipistrel's part. They wanted to make something that was very price accessible so that more people could get their hands on this thing and give it a try. So they made an LSA aircraft that fit in a pretty sensible price bracket. That really helped a lot of operators like ourselves take delivery of a few aircraft and learn what it takes to operate an electric aircraft. Our motivation was to learn a lot of lessons from that so that we could scale into bigger and higher volume and higher capacity electric aircraft in the future, of which there are not yet many other options on the market, although there's some very exciting projects in the wings that will hopefully come to market very, very soon with fully certified models. So back on the subject of the lessons themselves, operating an electric aircraft is fundamentally quite similar to traditional aircraft. There's most of the safety aspects and the learning aspects and the operational aspects are all in parallel with a typical aircraft. The big compressor is endurance, but depending on your airspace and how you handle it, and with good instructors, it's actually not a limiting factor too much. However, your flight training curriculum does need to be backed up by traditional piston engine aircraft of a similar airframe would be ideal, which is the pattern that we use in Australia. So we've got three electric aircraft, not all operating in the same location, but then we've got piston engine aircraft of the same airframe uh, operating in parallel with those aircraft so that we do what we can in the electric and we do what we can't in the piston engine aircraft. Particularly navigation flights are going to be required to be piston for a little while yet. But there are some very exciting emerging aircraft in the States from Bi Aerospace that will have a longer endurance that should address some navigation components for training. Now, electric aircraft goes far beyond training. That's the carrot that a lot of that's being dangled by a lot of the developers out there to operators to try and get them to uptake the new emerging technologies. And because your typical flight training lesson is quite short compared to maybe a longer flight, it does fit the cadence of electric aircraft charge cycles a little bit better. And we found that to be the case, definitely. Out of a single aircraft, we could easily fly 4 or 5 missions a day with the charge cycle. And we found the charge cycle not to be too disruptive at all. In fact, it was in some ways a little bit helpful just to fit in the cadence of the day. So a typical operation would be the pilot and student arrives early. The plane's already charged from a slow charge from the night before, of course. Pre-flight on electric aircraft is extremely brief. There's very little to check, no fluids to check. And because the aircraft doesn't vibrate in very modern build of aircraft, there's not a lot of hinges and points and flaps and things to check on the pre-flight. So very rapid. Out for a 40 to 50-minute mission in non-controlled airspace, but down as low as maybe a 35-minute mission in controlled airspace. And so some critical learning for the student and some particular operations on whichever lesson they're up to, and then back to the hangar for a charge cycle. We then found that that charge cycle is a perfect amount of time to debrief one student, rebrief the next student. Our briefings are typically about was actually quite functional and not very disruptive at all. In Australia, particularly where we are in Perth, it is very hot for many months of the year. So we had a challenge with keeping the batteries cool in the charge cycle and had to build some supporting ground equipment to manage that correctly. So we ended up building just a little custom rig of cool air management. So unlike an electric car, for those of you who have an electric car, you probably notice that the vehicle self-manages its temperature in the battery architecture. But in aviation, weight is our enemy. So there's as few components on the aircraft as possible, which means it doesn't have a advanced onboard cooling system. So we do as much as we can with offboard cooling systems while on the ground to help manage the battery temperature. And that made a big difference. So that will extend both battery longevity long term and for more cycles and more uses, but it also compresses the charge cycle and lets you depart for your next lesson or next flight mission with a lower battery temperature, which reduces problems in the air from that point forward as well. So in terms of, there's a valuable lesson there, and I'll touch on this a little bit because this is probably going to affect what you're planning and what you're working on a lot with your ground equipment and opportunities for operators to upgrade or be ready for the next generation of ground equipment. The cadence we found with operations, and we tested this in a few different ways, is that a Bowser style charging solution will probably not be something that suits many operators. Because of that charge cycle and the way you use your downtime, having some sort of like airport centralized charging location where an aircraft would park and charge and then the pilot and crew would walk away and do something else is probably pretty unlikely. We do have one of those setups at one of the airports that we fly to. It's a small island airport, and we weren't able to put some infrastructure in where we wanted to. So we put in some rolling infrastructure, some non-permanent, freestanding, grid-independent infrastructure, so a solar array mounted and built onto a trailer with some storage battery on board. And that was a fantastic solution for that island. But in using that, it was more proof of the idea that the a Bowser style or having the aircraft charging not at your home base is not very practical for an operator, whether you're looking at a charter operation or a flight school operation. That island that we fly to is one of our charter locations. So as well as a flight training school, we have a air taxi service, and we do a reasonable volume of probably about 10 to 15 air taxi flights per day. So we use that island destination as our test location for the electric flights as well. Though we weren't taking any fare paying passengers in those electric flights, we were just running the process to get the feel of how the cadence would work if we were carrying fare paying passengers. So the way we started describing it internally and how we plan things now with what we're forecasting for the future and how we're trying to set up our sites to accommodate better electric charging in the future with the bigger planes that are coming is we call the site a nest. So we plan on a nest for each of the electric aircraft where the aircraft will rest in its nest overnight with low speed, low temperature, low current charging cycles, which is good for the battery, good for the temperature of the battery, and good for the longevity of the battery. So the plane sits in its nest, its regular home where it's charging slowly, and then it begins operations but returns to its nest each time, where your ground equipment, of which there will be more than probably just a charger. We're going to be looking at most of these upcoming aircraft are going to have various off-board cooling systems, like the small one we developed for the Pipistrel, and some of the bigger equipment that we're working on for the next gen aircraft as well. So that's all kind of part of the nest. And it's going to be very hard for airports themselves to accommodate multiple aircraft manufacturers and their various cooling requirements, let alone charging requirements on their own. So the advice I've been giving to some airports in Australia that have been reaching out as well with a similar mindset, just trying to find out what they can do to make themselves ready or make their spaces more ready for the operators that are going to use the airports, is there's probably not much you can do for them in terms of direct equipment that it will be on the airport for people to use, because there will be a variety of chargers and variety of cooling systems for a variety of aircraft. And there's no central place you're going to be able to put them that will suit your variety of operators, or that's unlikely to be the case, I think, from our outlook. However, what you can do is make lots and lots of current available to them. And I cannot understate the demand of current that these next generation aircraft will put on existing grid and infrastructure systems. I've found, particularly in Australia, that the grid infrastructure at a lot of airports is quite dated. Sometimes 50 or 80 years old since it's had any sort of substantial upgrade, or maybe in some cases it's never had a substantial upgrade. It was installed many, many decades ago and hasn't been touched since. And there's no way that these old pieces of grid infrastructure are going to support a new wave of multiple electric aircraft trying to charge from the grid at once. So my advice would be to try and help however you can reduce red tape for some of the operators that are going to want to do some infrastructure upgrades. If you can help them with a pathway to store energy on site and quickly be able to increase their amount of stored energy with battery electric storage, of course, so that they can still be accessing the grid in a low current capacity, but have their stored energy to deliver to their aircraft in a high current capacity when they require. That's probably the most likely helpful, the most helpful thing you could do from a planning perspective for the operators, I think. I see this as a message in the chat. I did invite some Q&A along the way, and I think I saw something pop up before. So if anybody wants to throw a question in, please do.
Hey, Korum, I'll throw a question at you now.
Sure.
I'll jump in with questions. And yeah, a good quick reminder for the attendees, drop questions in the Q&A feature, I'll pop on or Jackson will pop on and we'll ask Korum those questions as we go here. I really appreciate what you're saying about the airport charging preparation side of things. I think that it's still incredibly early in the electric
Yeah,
aviation market, right? And there's a lot of different things that still need to be figured out in terms of how these aircraft are going to be integrated operationally for various types of operations, be it flight training, be it air cargo, air medical transportation, passenger transportation. And the difference in size of some of these airframes too, and the battery sizes is pretty significant. You could have a
yeah,
hybrid electric system with maybe like a 30 kilowatt hour battery versus a bigger aircraft, maybe capable of carrying like 1,500 pounds that has a 250 or 300 kilowatt hour battery, and the charging requirements for both of those look very, very different, right? And the cooling
drastically
side
different.
is, it's its own beast. It sounds like a lot of
Mm.
what you were talking about is almost treating like the airport as like this like big energy node, where it
Yes.
really is focused on like energy management, energy planning, and providing
Mhm.
that in a way that is helpful for operators. Would you kind of agree with like that characterization of like a need to just focus on like energy management from like the airport perspective more?
Yeah, 100%. So just making energy accessible to the operators and reclaim of energy as well, or renewable energy access. So we have had some challenges at one airport in particular with installing solar, which is a shame because there's so much solar energy falling on the ground in Western Australia every day. It'd be silly not to collect some and store it away for later. So, but we had a bit of a fight for quite some time with the airport to install some solar. So that sort of obstruction for operators is frustrating. They'd probably like to just move ahead with a new way of doing things and to have those sort of silly blockages, because of a form hidden away somewhere in some bureaucratic process, which is
Yeah.
stopping a practical integration of some new equipment. So if there's anything you can do to smooth that pathway, but I have heard of some European operators having a huge problem with getting permission to store batteries on site as well.
Mm,
So to then draw slowly from the grid or to store their own renewable energy that they've collected, they weren't able to store enough energy because they couldn't get permissions to have particular storage on site. So anything you can do to prepare for that. Another reason why I'd shy away from doing any specific infrastructure is just the speed at which things will change and at which new iterations will hit the market.
yeah.
If you were to do something too specific in the early days, it might only be 12 or 24 months before that becomes redundant. And then a new system is happening. So, I've just lost a lot of my light here. Sorry. I'll keep talking in the meantime. Uh, Whereas if you're just making a pathway to a lot of accessible energy for the operators as they change and upgrade their equipment, or as people shift from just pilot training into passenger operations, or like you said, different aircraft are coming at different sizes, then providing with what they really need, which is just access to energy, and they'll sort out their own equipment
Yeah.
specific to the aircraft they're flying.
And it makes me think of too, I don't know what country or what country this is in. It's I think a Scandinavian country, maybe it's Norway, but there's an airport there that has been progressive, and they put in something to the effect of like a 1 megawatt kind of like
Yeah.
energy hub on the airfield, and
Yep.
then they're ready then to kind of connect that 1 megawatt hub to various different like ramp spaces
Yep.
along the airport for like operator specific charging needs. And so
Yeah.
they have a big flight school there. Again, I think it's like the Green Flight Academy and what they're doing.
Yeah.
And so that's one that stands out to me as like, focusing on the energy management side of things and then positioning charging near the operator, which, like you're saying, sounds like it's important.
Yeah, absolutely. Just making bucket loads of energy available to your new and existing and potential future operators as well at any of the sites you're developing. Something else to keep in mind, aircraft aside, our energy demands, our electrical energy demands are not going to decrease at all. Uh,
No.
Even without the aircraft, there's going to be a lot more ground requirement for electrical energy. I know there's been maybe a little bit of a wind back from what I see from over here of electric car uptake in the States, but I don't think that will last long. The trend will continue and electric cars will continue to roll out. So there's going to be huge energy demands on both the ground. Everyone's ramping up more compute power day by day in their operations. So people are going to be plugging in more pieces of equipment than ever before. So just the ground side energy demands at every airport and, every industrial area and park is going to continue to climb. So the more you can do to open up easy channels of energy and less red tape for people to collect and store their own energy or be a part of a grid tied system, then you'll just be supporting the development of these operators. And I guess what's important to you guys is attracting more tenants and attracting more people to come and do business at your sites, which I'm sure is important to you.
So we have a question that came in chorus, Korum,
Yeah.
and the question was about ideal temperatures for each nest in this kind of nest concept.
Yeah.
And so for me, I think there's a question of like, where do you envision the nests being? Are they kind of like all located and situated in a hangar? Are they positioned on like the ramp space adjacent to hangars or facilities there? And then if they are positioned on kind of a ramp space adjacent to a hangar, how much does temperature matter for each of these nests?
Yeah. Look, the temperature in the aircraft can be managed with ground equipment. So that's the ambient temperature around isn't too bad, whether it's cold, even like sub-zero, or batteries will typically, it's going to vary from different battery technologies that come out, but as a pretty broad brush stroke, it'll be very typical that most electric aircraft batteries are going to want to exist between 15 degrees Celsius. Sorry, I don't have off the top of my head Fahrenheit conversions, so you guys will have to do that. 15 degrees Celsius up to about 40 degrees Celsius. And that will be typical for a lot of battery chemistries for the foreseeable future. So the aircraft, there we go. There's a little a Fahrenheit conversion coming in there in the chat.
Yep.
So some of the aircraft will have onboard equipment to help manage and keep their batteries within that temperature window. Some of them will need the off-board equipment.
Yeah.
The off-board equipment is where we start leaning back into the nests, where those nests are probably going to want to be hangar-based. A lot of this equipment won't necessarily be weatherproof, and to make it weatherproof makes it more costly or requires more ongoing maintenance. And while that won't be aviation scheduled maintenance because it's ground equipment, it's still going to be work to do that the operators are going to do, and having to make the equipment a lot more robust. I'm sure everyone's come across a few electric car chargers that are out in the weather all the time. They've just completely fallen apart. Operators aren't going to want that sort of thing happening with aviation. They're probably going to want to keep a lot of their equipment housed and inside. That being said, it doesn't necessarily need an entire hangar to do that. Maybe it just needs a small pod of protective weatherproof shielding, like a small little, I was going to say shed, but want something a little bit nicer than a shed probably, just to house the ground equipment that's going to support the aircraft. But again, most aircraft will be adopted by a single operator that's integrating a single or a couple of aircraft to their flight school or their charter operations, and it won't necessarily be other operators on the airport at first. So they'll probably self-manage and create their own nests within their own hangar space anyway, if there's enough hangar space. I know some airports operate with limited hangar space, and a lot of people use apron parking. That's where I see it being a challenge, because I think people really will want that. Slow charge is important, and you'll want to do a slow charge most nights that the aircraft's active, and that opens up, you don't want that out in the weather. There's the potential for liquid ingress in the charge connector and the ground cooling equipment, any supporting equipment. And then, of course, just the risk of sabotage, theft, damage, equipment that's out and exposed. I don't know how much that's an issue, but for some regional airports in Western Australia, it is an issue. People steal copper cables all the time. It's super annoying. So the more things are kind of tucked away and out of the weather and protected, the better, I'm sure. But of course, that's not always practical. So that'll be a little ongoing challenge, and I'm sure there'll be some heat between operators and airports on that subject over the coming years.
Yeah. Yeah. Okay. That's great. For the Pipistrel Velis Electro Quorum, what is the kind of like charge requirements, if you will? Three-phase power. What kind of
Yeah.
voltage and currents, and just like overall power level are you needing for those? And like, what does that look like?
Yeah, so the Pipistrel Electro is probably the smallest electric aircraft that will ever be. I don't think anyone will make a power system that's lower than that, except for the launch assist gliders that you see.
Yep.
But for a purely electric propulsion system aircraft, the Pipistrel will probably be the smallest ever. So, and we're already having current challenges. So, specifically to that aircraft, in Australia, we do a three-phase 240 volt, 63 amp power supply is the ideal one. There's various chargers available, just like a car charger. There's small ones that you can plug into a 10 amp power outlet. It charges the aircraft very, very slowly. Or the largest of the Pipistrel chargers charges at about 20 kilowatts, and
Yep.
it requires that 63 amp 240 volt three-phase power supply. Now, just accessing that amount of power in airports has been a problem. There are very few three-phase outlets around on a lot of the Australian airports from that aging infrastructure I spoke about. Uh, I'm hoping that's not the case for you guys. There's hopefully a lot of operators that have big three-phase compressors or welding equipment already that already need that high current power demand, and that's the case definitely in some locations. So the power is usually around, but again, like I said, that's the very smallest electric aircraft that will probably ever be, and we're already feeling the pain of limited energy availability. The next gen electric aircraft they'll want sometimes some of them will want maybe 8 times that amount of power
Yeah.
for a 1 hour charge cycle. And that's just one aircraft. If you've got 4 or 5 of those on your airport and they're all trying to access energy at once, all of a sudden you've got a really big energy demand problem. So, yeah, just expect huge requirements from some operators as they start to adopt these aircraft. The good news for you is you won't see like 100 of them hit the market in your local area at once. There's going to be unique operators that adopt 1 or 2 aircraft for a year or two before they ramp up to a fleet. So you will have a lot of time to work through this. I don't think it's going to be an immediate and critical challenge for you all at once.
Yeah, I appreciate that, Quorum. I'll ask another question, which is
Yep.
just kind of more like a high level, like broad, kind of like getting your thoughts and perspectives. Just like talk about the kind of flight training experience from both like the student perspective as well as the CFI
Mm.
perspective, when it
Yep.
comes to training in the Pipistrel Velis Electro and maybe what you're seeing in the future OEM market opportunities with aircraft that are coming to market. And then, in addition to that, talk about kind of the progression of that experience as you've become a little bit more mature with your business and your
Sure.
operations, and you've kind of really gotten a good flow and learned from a lot of the early challenges that you probably faced in doing this.
Yeah. There's a classic entrepreneur arc of uninformed optimism is stage one, where you've got what you think is a fantastic idea. You're very optimistic about it, and you don't have enough knowledge yet around the subject, and
Yeah.
you go into it like a bull in a china shop and try and get a lot of things done. And then that really hockey stick shaped curve of excitement gets tapered off and comes back down into the realm of reality with informed optimism, where you're still optimistic, you still like your idea, and you spend so much money on it, you can't back out of it now. But you've now learned some lessons, and you're operating a little bit more practically and starting to really understand what you can and can't do with the equipment. So I followed that curve classically, very uninformed optimism. Bought a couple of planes, was convinced we were going to change the world in 5 minutes flat. And then we learned all the lessons. Now, probably the biggest one to shorten it as much as possible and put it into a bite-sized piece of advice is controlled airspace and non-controlled airspace going to be your friend and foe in that in the opposite order. So a non-controlled airspace is much more practical for electric aircraft use, and it's all down to the endurance. With the controlled airspace that we have been testing and working in, it's a very busy airspace. There are fire bombers and other emergency services operating regularly, and they take airspace priority. So it's not uncommon for you to reapproach the airfield, and you'll be sent on an odd traffic pattern to make room for some of the emergency services coming in and out. Now, when you're running on bingo fuel and you're coming back with very limited endurance and limited reserve, you don't have a lot of spare to accommodate that. So that takes some extra planning. And also, in the case of training, you've got students that are not landing well.
Yeah.
Maybe one go around up your sleeve. So if you're working with a student, you're at a student level, or you're in crosswind and there's a high likelihood of a go around, you have to compress your mission to accommodate that. Now, when you're in a non-controlled airspace, things get a lot more accommodating. Particularly the Pipistrel aircraft and a lot of the emerging electric aircraft that will come to market will be very, very efficient, very high glide ratio, very slippery airframes. So you can use your height and speed as I'm out, and we're doing medium terms at 3,000 feet upwind of the field. And then we finish the lesson and we plan to head back to the field. You cut the power and glide back a couple of miles to the field. So your energy profile on the return and approach to the airfield is almost zero, which is fantastic. It means it's not working the batteries hard, they're cooling, you're saving a lot of energy, and you've got more up your sleeve for a potential go around. You can also join the traffic pattern in whichever direction you want to integrate to that with minimal energy. So that works really well in non-controlled space, and it dramatically extends your lesson time by maybe 5 or 10 minutes. But then in your controlled airspace, where you're having to approach from a particular vector as decreed by the traffic controller, you might be flying 4 miles towards the field into a 25 knot headwind because you have to approach from that direction. And that's just how it is. And that's a problem for your limited endurance. So that's where it starts getting risky. If the operators and the CFI and the trainers aren't planning well for that and accommodating that, they could get themselves into some trouble, might have to call a low fuel mayday. And, there's not this sort of good news story you want around an electric aircraft having to take priority over other traffic just to come in for a safe landing. So lots of critical planning so that they don't end up getting in anyone's way and being a pain in anyone's ass. That's the critical planning around there. So I'd recommend non-controlled airspaces for people. They'll just get a lot more value out of the aircraft and have a lot less chance of becoming a hazard for larger aircraft or emergency aircraft or aircraft that do really need the priority.
Okay, that's great, Korum. Appreciate that. Can you talk a little bit on so kind of like going back to like the first part of the question, student experience, CFI experience. What have you noticed from both of those ends in kind of the experience in flying the Pipistrel Velis Electro versus some of the combustion engine aircraft that you're using for cross countries and navigation flights and things like that?
Yeah, look, the flight experience in the electric it's nice. It's really nice. No vibration, very little noise. It's a much more serene flying experience, particularly when you're in really calm air. You feel like you're ice skating up there. The Pipistrel airframe is very clean. There's not a lot of disturbed airflow, so it's just a really smooth and delightful flight experience. That can be said for some of the more modern aircraft as well, like a Diamond or a Cirrus, that they feel really, really nice. But not everyone can afford a Diamond or a Cirrus. There's still a lot of old traditional aircraft out there. So the difference of flying a nice new electric aircraft is profound. And I definitely prefer it. My preference is to fly the electric, and I typically do. The pre-flight is, you feel a little bit guilty. There's almost nothing to do. You just kind of get in the plane and go, which is really nice as well. And not having to get your hands oily, checking a dipstick or topping anything up. So that's really, really nice. I think from the trainer and the CFI's perspective, that's actually been a little bit of a concern, because that time before the flight and that time at the holding point or in the run-up bay, is a good bit of time for the student to sort of get their head settled, do some final checks, maybe get their head right to do their radio calls. And it can feel a little bit rushed in the electro because you do kind of just jump in. There's very little to do before you can depart. So what we've added into our process was just some stops. We'd still go to the holding point, stop, do some final checks. There's nothing to check in terms of the propulsion system, but it's mostly just that moment and a few deep breaths for the student and to do some checks of themselves, their doors, their hatches, harnesses, things like that, before they get to the holding point, and just to give that little cadence still. So that was something that we only had to go out and fly a handful of times to figure that out. And operators will do this for themselves. I'm sure there's a lot of fantastically experienced CFIs and trainers out there that will see these little patterns emerge straight away, and they'll put their own little bits of process in to accommodate that. But definitely, it's a very addictive experience flying electric. It's hard to jump back in a petrol engine after you feel a bit silly. You're like, who would do all this with the noise and the smells and the oil? And
Oh, just the work involved. I get it.
Yeah.
Everything you're saying to me resonates when I was going through my PPL. So we got another question from the Q&A, and
Yes.
I'll just read this out verbatim. Is there anything specific that your students have noticed in terms of difference in performance of the electric aircraft versus, again, whatever the conventional combustion engine aircraft is that they're training in? And the question goes on to say, is it hard to make that mental switch between flying those two airplanes, and how do you approach making that switch for those flights?
Yeah, in terms of making the switch, not difficult. The pipistrels, they've been well built to be very well mirrored. So the position of all the controls is almost identical. The instruments is almost the same. So particularly with the pipistrel, when we jump from the ICE pipistrel to the electric pipistrel, there's very little for the student to adjust to. The only thing I'd point out is there's probably more emergency procedures to be aware of and a little bit more to monitor in the combustion engine. There's the system, the way the system reports to you in the electric aircraft is very simple, and it monitors everything on one screen. So you've got one thing to look at, and it's got some nice, sensible little bar graphs that'll just tell you whether anything's outside of its normal operational threshold. Whereas the piston engine aircraft, depending on whether you're going in a really different one, we've got two Cessna 172s in our fleet. One of them's quite old, and that thing, you're having a look at so many gauges, and none of them read correctly. So there's a lot. The workload to monitor the health of that aircraft in flight is a lot higher than the nice new Electro. So that's something to definitely be aware of. There's a risk that the electric makes you not lazy, but maybe complacent because you've got so little to look after. The other thing which some old aviators sort of brought to my attention is they're used to a hum and a vibration, and that seems normal for them, and they feel uneasy if there isn't any noise. It's the opposite way around in the electric. So you hear almost nothing and you'll feel almost everything. So it actually helps give you back some feedback from the airframe if something's not quite right. If there's a bit of play in an aileron or a rudder, or if someone's left their seatbelt not a little bit out the door and the door's closed, you'll feel the tap, 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 the lightest little tap that it is. You'll feel it through the airframe as you're flying because there's so little alternate vibration. So you do get a lot of information back on the airframe on the Electro. There are some different safety things to manage. The electric aircraft does have a little more thermal management on hot days, certainly. And it wouldn't be a problem on cool days. In fact, you'd welcome a cool day if you're flying around in 5-degree air at a couple of thousand feet. That'd be absolutely fantastic for your batteries. The batteries will be producing their own heat. They're exothermic during the discharge cycle. So as you're flying, they're creating enough heat to keep themselves within their temperature range. But when we're flying on very hot days, our threshold was a 32-degree day on the ground. If we're 32 degrees Celsius or over, we're not going to be able to fly the electric for very long. You can go fly it solo with a little bit less load and climb a bit more gently, but you just find the heat rising on the batteries very quickly. And you could fly it and continue to fly it. You'd still be within the operational threshold, but you're now putting the batteries at a stress point and shortening their life. So just like a regular plane, you don't want to thrash it. You want it to last as long as possible. You're trying to do as few starts as possible, um, to go easy on your starter motor. While starts aren't a problem in the electro, you are trying to manage your thermal envelope very well, which is going to extend the longevity of your batteries. So it's not so much that it's harder or less hard or problematic. It's just different things to pay attention to. But that can be said from when you switch from piston to turbine anyway. It's a whole different set of numbers and figures and thresholds that you're looking at. So there's just some difference training involved, and it's a bit of a process that most pilots will have to get used to in their pilot career anyway as they switch from aircraft to aircraft.
Yeah, and you brought up a couple of interesting points that I want to, kind of follow up on a little bit more. One of those is on just like if you were to have kind of a battery overheat while you're flying, and I'll come back to
Yeah.
that one. And the other one is on the just battery state of health side of things and
Yes.
cycle life and just managing that as an organization. I'm gonna start with the first thought, and then I'll come back to the battery state of health question. But like, let's say that you were to exceed that battery kind of critical temperature, getting into the red arc or red
Yeah.
red portion of the chart as you're flying, right? You hit that 40 degrees Celsius line, as you said. Is there things that you can do in flight to actively bring that down? And are
Yep.
those kind of like the emergency procedures that you'd use?
Yeah, yeah, definitely. So, as with all aircraft, height and speed is your friend.
Yeah.
So we get to a bit of height during our mission, so that we've got the option to descend and at moderate power if we need to de-stress the propulsion system for any reason. Now, the batteries won't spike rapidly, right? It'll be
Yeah.
a developing heat problem, so you can manage that in real time, and you'll see the battery temperature sort of beginning to extend to the threshold of the envelope long before you exceed the envelope. So you can really start managing early. And the thing to do is just reduce power, reduce speed. Um, Again, the Pipistrel is a very clean airframe with really wide wings and has a 16 to 1 glide ratio. So
Wow.
you can come back on the power a lot and bring the power right down and still have just an arrested rate of descent or a nil rate of descent, and maybe be trickling along at 55 knots with the power at maybe one third or less. And that's still getting you quite good airflow over the batteries, but with a very low current discharge, so they're not generating a lot of heat internally. So that's one way we can sort of modify the batteries. But if it's a high temperature, you've climbed a couple of thousand feet and you've only had a reduction of 2 or 3 degrees in your climb, which is some of ambient air, which is sometimes the case. You're not going to get great cooling, and you need to be ahead of it. So.
I see.
Just a little bit more planning and a little bit more awareness around that. And if you're unable to maintain your temperature and is consistently climbing, abort mission, return to the airfield.
I see.
Or you're just going to cook those batteries, massively shorten their life, and your engineer will not be impressed.
Yeah, so if you're ripping it up in the pattern, and you're seeing the battery temp rising with every lap on the pattern,
Yeah.
maybe just bring in for landing instead of doing another touch and go where you'd really elevate it on that takeoff and climb portion of the flight. Whereas if you're at
Yes.
altitude, glide in, pull the power back, it'll kind of self-regulate a little
Yeah.
bit. Yeah. Okay. That
100%.
all makes sense.
I'll just touch on that quickly too. You mentioned traffic. I'm sorry. You mentioned circuits, and what we discovered. So when we first bought the aircraft, our initial thought, and this is what Pipistrel promoted a lot as well, was great. These are things going to be perfect for circuits. That kept everyone very comfortable because we weren't going very far from the airfield, so no one was worried about endurance, and range anxiety was mitigated. But what we discovered in the performance and the health of the battery, and this will be typical for a lot of other emerging electric aircraft as well, each rather than first we started managing the battery with an expectation of charge cycles, and that's how we were going to measure the life of the battery. And we thrashed through the first set of batteries, uh, counting the discharge and the recharge cycle as one full cycle with an expectation of how long that would last. What we ended up discovering with the data from the batteries and talking more to battery engineers and battery manufacturers is the way that the batteries are being treated in the electric, well, in an aircraft by a full power application for the first 90 seconds of flight, and then coming back to 75% power application for the remainder of the climb, and then coming back to about a 50% power application for cruise. It kind of worked out a little bit more that each climb was a battery cycle rather than each battery cycle being a battery cycle.
Yeah.
And we didn't find that out until a good 18 months into some fairly heavy operations. And by that time, we'd been focusing really, really hard on circuits. But circuits, we'd go out and do 7 or 8 circuits in one session, and that ended up being 7 or 8 cycles effectively,
Wow.
because we're discharging at a very high 3C discharge rate with a battery system that has limited thermal management, just because of the nature of aviation. We can't carry a lot of onboard thermal management, and it's only heat exchanging with the ambient air.
Yeah.
And that that had really compressed the life cycle of the batteries. So what we started doing in the remainder of our training, we've actually shied away from circuits in the electric plane, and now we do a lot of anything where we're climbing to height and then sticking to height. So even climbing and descending is fine, and managing turns, but we started using the electric a lot more for consolidation rather than the heavy ab initio training, uh, because there's quite a few lessons that require some a lot of power on off application during
Yeah.
the ab initio. Stalls are very energy intensive,
Yeah.
the circuits, of course. And then what we also find with the student is they're making their inputs on the controls are less smooth and can be, so they're not managing the aircraft as well. The aircraft's often out of balance. So things aren't working as efficiently as you'd like them to. And when you're up there with limited onboard energy like you are the electric, every little scrap of efficiency really, really counts.
Yeah.
So it almost became that, all right, the electric aircraft isn't a beginner's aircraft anymore. It's something we want to move someone into after they've got a handle on how to manage the aircraft a little bit more, after they're less likely to need to go around, and after they've got their landings mostly sorted, so that we're not having to do so many climbs. If you can
Oh,
go out and do one climb per flight mission, then you're getting one whole battery cycle. But if you're going out and you're doing 3 or 4 climbs per flight mission, you're kind of eating up 3 or 4 of your battery cycles in that one charge cycle.
yeah.
Um, yeah, so this and that's all early days with a one type of battery chemistry and one type of inverter. So it's going to be different from aircraft to aircraft. But we have been working with a few of the other aircraft developers and passing on these sort of lessons and knowledge. I think we've done, apart from someone you mentioned before, E-Flight Academy,
Yeah.
and there's maybe 1 or 2 other operators around the world now that have caught up a little bit. But in a year ago, we were probably one of the highest volume electric aircraft operators. We've done over 1,800 passenger movements, over 1,300 hours of flight. And so we had this really good data set of all of these different conditions and places and airspaces we'd flown in. And that's the trend that we were finding, that the climbs were our problem, not our battery cycles.
Yeah.
And we'll be really careful with other aircraft as we get them in the future, the next gen aircraft, which should manage that a little bit better, but it's probably still going to be a sticking point. So climb as little as you can in your electric planes
And
would be
and
my
there's a lot
advice at
of
this stage.
like it depends too, just in future generation aircraft, right? Certainly, like a 3C discharge rate on a battery will
Yeah.
absolutely stress a system. And if you
Yep.
don't have great thermal management to go along with that, I mean, I could see how that would really fatigue a battery really quickly. If
Yeah.
you can do a takeoff though at like a 1C discharge rate, and maybe there's some enhanced thermal management on board or whatever that looks like, I think that you'd at least mitigate some of that fatigue and battery impact there, which is good. And
Yeah.
you're probably excited for future trainer generations that are maybe more capable of operating in that kind of cross country
Mhm.
phase of the flight training program and doing some of that
Yep.
navigation work, right? Because it seems like that's a great fit on paper for what you'd want to use an electric airplane for, given
Yeah.
some of those concerns that you talked about.
Yep. we've actually got a 6-seat hybrid electric aircraft project. We have a full flying prototype in Western Australia, and we're playing around with some new drivetrains in 2026. We all the design work we're doing on that now. It's a clean sheet design. It's not a retrofit of any existing airframe. It's a very efficient airframe. It looks a bit like a giant pipistrel, just with 6 seats, which is what they need to be, right? Very sleek, very low drag, and very high L over D. And we are massively overspecking it. So to your point, we'll want to get closer to a 1.5C discharge at light load. So if you've only got 2 passengers on board, you'll climb out at a very mellow 500 feet per minute at a 1.5C discharge and be really low load on the batteries for longevity and for the thermal management system. And then maybe at high load, only when you need to get a more rapid rate of climb to get over a particular obstacle. But you'll put that extra power on knowing that you're compromising the battery health and the state of health long term to get the required climb today. So it's something operators will need to be critically aware of. But yeah, we'll be speccing that hard, and that's a full hybrid system as well to manage all the endurance challenges. So what we're trying to do is land on an aircraft that, pardon the pun, land on an aircraft design that will actually suit all applications. So typical sub 1 hour charter applications, and all with 4 or 5 passengers on board, and then all navigation requirements with 2 passengers on board, even with maybe 1 stopover in the navigation flight for a little top-up charge. And all very doable. As long as you've got a bigger, more accommodating airframe, you can get enough onboard energy there to get back down into that sort of 1 to 2C discharge on climb, instead of where the pipistrel is designed for that 3C discharge on climb, which really does punish the battery system, unfortunately.
I'll give a quick reminder for the attendees that feel free again to drop in any questions as you go along here. I have a lot more interesting questions I'll keep asking Korum, which I think will be beneficial and useful for the folks that are listening in. But as you have questions, drop them in. We'll hit those. We'll ask those as we go here. One thing that you and I, Korum, we've talked about kind of beforehand that I think it'd be helpful to touch on now is this idea of like a retrofit solution of taking the electric propulsion system and putting it on something like a Piper Warrior or whatever the existing airframe is versus the clean sheet design approach. And there's companies operating in that space like Bio Aerospace who you talked about. Can you just talk about like kind of like your thinking behind like the retrofit and clean sheet and just any thoughts as it relates to that?
Sure. Yeah, we're definitely pro clean sheet, and we've looked at retrofit options, as have many, and a lot of people have tried. I know everyone really wants to retrofit because there's so much certified equipment out there, and the only thing they don't like about it is the piston engine on the front of it. So it's very tempting to try and salvage a lot of that equipment. There's also people have spent a lot of money. There's a lot of capex gone out to acquire all of this equipment, and the idea that they just sort of become redundant or no longer economically operable is it's an awful thought, but it might just be the case. Unfortunately, when a lot of these aircraft were designed originally, efficiency wasn't high on the list of priorities. Priorities were more around manufacturing capacity, efficiency in manufacture, and that lent to particular shapes that went together quickly and could come out of a production line quickly, but weren't as necessarily as efficient. And the solution at the time was, because there was no such word as emissions and fuel was very cheap, and people weren't really thinking about a scarcity of fuel and a management of emissions. So they just put more horsepower on things. That was the solution to every aerodynamic problem, more horsepower. And that's how a lot of these old airframes were unfortunately designed. And then when you switch to a system where efficiency is so very critical, because every gram that goes on in the aircraft is not as convertible to every gram of energy that goes on board the aircraft is not as convertible to thrust as liquid fuel is, then, and you're carrying that weight around with you for the whole flight profile as well, you don't shed any weight during the profile, then you need every rivet gone. You need the sleekest, smoothest shape and flow of airframes and very clever wing designs and retractable gear if you can, but that adds a lot of weight. So, spats on gear and smooth undercarriages. And that's just not the case with a lot of the old aircraft. I mean, are some out there that are getting close to it. Things like a Cessna Caravan is maybe got a potential for a good conversion. But you mentioned the Piper Warrior. I mean, we've got 3 Piper Cherokees in our fleet and training and charter fleet, and they're such a pig of a thing. There's no grace in them. They really do like bash their way through the air, and to try and put a electric propulsion system on an airframe like that, 100% it'll work and you'll get it to fly, but there'll be so much wastage in the shape and just inefficiencies in the airframe that you'll lose a lot of your already limited endurance. The other problem with getting these retrofits happening is you won't be able to put the components exactly where you'd like to for cooling, safety, and minimal cabling. So you're going to have to compromise on positioning for weight and balance and just to accommodate structural components of the aircraft as they are now. So you'll probably end up adding a little bit more cabling and then maybe needing a little bit more cooling management because things aren't right where you'd like them to be. So it starts becoming quite expensive because you have to do a little bit more work, and that's another compromise in the architecture of the design that might limit the performance again, as well as the airframe. So you start having all these setbacks, and then the overarching thing for me, it was an easy decision for me. I've had to come up with these arguments to go through with my team, and we debate these things internally and with other people as well. But the biggest one for me is I think it's time to work on the next thing in general aviation. I don't think we should be putting a lot of energy in trying to prop up 50-year-old aircraft designs to get them flying for another 20 or 30 years. The rest of the world has moved on rapidly with technology advancement. We don't try and sustain 50-year-old cars to drive them around as our daily drivers and make them efficient. We just do the next thing. And I think that's important for general aviation too. It's so expensive for certification, and I know it's hard the cogs to move the cogs in aviation. They're big, they're heavy, and they're expensive, and it's difficult to put a new design out there. But it has to be done. We just have to move on to. We've got these amazing new fabrication methods now. The way carbon composites can be laid up, and with modern methods, is just fantastic. We can build much smarter airframes with all the components exactly where they need to be. We can make them safer and more comfortable. Safer is a critical component too. Any new aircraft is going to have a ballistic parachute built in, which is a really good idea. And it's just not going to be practical to put that in many retrofits. So all of these new design elements can go into the new aircraft, and we just make some really modern, really efficient new birds with a lot more safety and comfort characteristics. And then efficiency characteristics as well, which is going to aid our transition to hybrid or electric propulsion systems.
I love it. Thanks, Korum. We're running up to the end of time here, so maybe I'll ask for one final 30 seconds of just thoughts, advice as we move forward to the future of flight training with electric airplanes.
Yeah. It's I think it needs to be done. Certainly, it's quite achievable. We're right on the cusp of it really occurring. A lot of developers have been putting many, many years into making it happen. The Pipistrel was a toe in the water and just really dipping it in. It is a fantastic aircraft and it will always have a place. I don't think it will become redundant anytime soon. Its price point is fantastic. It's priced at maybe 1/5 of the cost of any of the other emerging electric aircraft that are coming out, at least a quarter. So it's always going to be the go-to for new operators to start and try testing, and for a lot of recreational operators to fly electric where they can fly. You really can fly up to an hour on your own in good conditions in the Pipistrel, which is a lovely amount of time to fly recreationally. So it will always have a place. You'll find operators adopting the electric aircraft for sure. The minimization and disruption on your maintenance side of the operation is profound. 100 hourly checks in the Pipistrel, they take less than 90 minutes. So we do it in a charge cycle. So the aircraft isn't even out of service for that day. And again, that's just due to most of the components are non-serviceable. The battery is non-serviceable for 2,000 hours. There's nothing to pull apart and inspect. The inverter's the same. And the batteries are checked flight by flight. So everything's quite fast and easy to manage. And that will get more attractive. There's always going to be the bias that hangs around, and it will be the case that some operators will have to age out before they adopt new tech. And that's just the way of the world. You see it in every industry. There are some operators and some businesses that will just keep doing what they're doing until they retire or bankrupt. Mm-hmm. And it'll be the same in general aviation. But some operators will adopt the new equipment. They'll have a good run with it. They'll probably learn some expensive lessons along the way. Unfortunately, that's just the way it goes when you try something new. There's always going to be mistakes. But I hope everyone sticks with it and hangs in there, because once you get your head around it, and it starts to feel normal, you wonder why it's taken so long to transition to something new, because the next gen electric aircraft in particular will really open up that opportunity for operators. They'll be running into less endurance problems, less operational management problems thermally and things like that. And there'll be more people having a really good experience with electric aircraft. So hopefully that'll accelerate it a little bit, because it's a pretty cool way to fly. I recommend it.
Appreciate it, Korum. Thank you. Jackson, over to you for some closing remarks.
Yeah, just a couple final things for everybody here. Korum, first of all, thank you very much for your time today.
No, my pleasure.
As well. Thank you to all of you for tuning in today. I dropped a link to the evaluation in the chat. Please take a couple moments to fill that out. That is truly very helpful to us for planning future programming. And second, details for the next webinar on December 18th are still being finalized, so expect details for that soon, but it will be a flight training focused webinar. And again, that will be on December 18th, and hope you can join us for that. So with that, thank you everybody one more time, and enjoy the rest of your Thursday.